Okay, so welcome back to another video. So we have a pretty basic improper integral that you typically would see something like this in a Calculus 2 class. We have the integral from negative infinity to positive infinity of 1 divided by x squared plus 1 dx. So you can already guess at this point like how to solve such improper integrals. So yes, we will be tackling that, but there's actually going to be another way we're going to solve this as well. So basically this video is going to be, we're going to be solving this integral in two different ways. The easy way, and say it with me, the complex way. Complex, we're actually going to be using residue theory to compute this integral and show that, from the two ways we solve it, that they indeed come out to the same answer. So the complex way, of course, being the interesting and the fun one, hence why this video exists for a reason. But I just wanted to show the little baseline on like the basic on how to solve this using in terms of limits, and then we get into like the fun part. So that's basically just the gist of that. So why don't we actually just jump right in? So from this given integral over here, so I'm going to write the same thing as given 1 divided by x squared plus 1 and then dx. Of course, when you learn in terms of linearity, when breaking up the bounds, we can break this up to say that this is the same thing as written from 0 to infinity of our same integrand. So I wrote 1 plus x squared. Usually that's okay since it's the same thing written as above, but I'm just going to keep it consistent, so write as the way it is. And then break this up again, so this time we have the bounds from negative infinity to 0 of the same integrand. Now, of course, that this is actually going to converge to some value if and only if these two integrals converges. So we're actually going to break this up together. So first, let's actually calculate the first one. So that means the integral from 0 to infinity, 1 divided by x squared plus 1. Now, we actually know that's the famous antiderivative of the inverse tangent function. So, and first, let me actually first write this in terms of a limit on how you actually tackle with such improper integrals of any kind. So we write this in terms of a limit. So the limit as b approaches positive infinity of our integrals. So this is actually treat this like it's finite, for example. So from 0 to b of 1 divided by x squared plus 1 dx, then simply that's the limit as b approaches infinity of inverse tangent of x. Evaluate this from positive infinity, 0 to positive infinity. This being, of course, 0 of that input is actually just going to equal 0. You plug in infinity, this being, of course, that when you graph the tangent x function, just tangent x, for example, we have these asymptotes that it lies between negative pi over 2 and pi over 2, but taking in that inverse, it's actually a bounded function lying in between negative pi over 2 and pi over 2. Of course, taking that to infinity, that's actually going to approach pi divided by 2. So that's one integral down, so let's now tackle the other integral. So as you can already guess, this is basically the same format and technique that we'll be actually solving as x squared plus 1 dx. Simply the same thing, we'll write this as a approaches negative infinity of our bound from a to 0 of 1 divided by x squared plus 1 dx. This being, of course, so the limit as a approaches negative infinity of inverse tangent x, and evaluate this from 0 and then to a. So I'm actually changing it. That's supposed to be a b over here. You put this for b, so we have inverse tangent b, then take that to infinity to get this value. So do the same thing here, of course. So plug in 0, that's going to be 0, and then minus, so inverse tangent a, take that infinity or negative, take that as a approaches negative infinity, that being, as mentioned, that's going to be pi over 2. So with this being the case that we have pi over 2, add that together, we get that the answer is simply just pi. So that is our answer for this basic rational function of the improper integral evaluated over the entire real line. So with that being the case, that's the easy part. So now let's get into the complex part. Okay, so now getting to the complex part, as mentioned, we're actually going to be using residue theory. So specifically, we're actually going to treat this by using contour integration. So what we'll use is that we're going to define some contour over the complex plane. Specifically, we'll actually be putting this for the upper half circle of our, so our contour will be the part of the upper half circle with radius r. We want to consider our function f of z being analytic of 1 divided by c squared plus 1, okay? So we consider that. So let me actually first draw out this contour that we're actually dealing with. Okay, so here's our contour that we'll be dealing with. I actually denote this as C, And we're actually evaluating this, well, integrating this, of course, on positive orientation, the counterclockwise, aka. So we have to break this up into terms of the bounds. So first, we're actually dealing with the real axis from -r to r, and then we have to evaluate this from our little arc length of the semicircle over here. We call this, I'll just denote this as C sub r. So that's what we have to do. So basically, if we're actually dealing with the integral, so the contour integral of, so positive orientation of our bounds C of f of z dz, so we actually break this up as the following. So we have the positive infinity to negative infinity, and of course you can write that as terms of a limit as well if you want to, of f of x dx, and then add this with the integral, so the contour integral specifically at this semicircle arc length over here, so c sub r of f of z and then dz. Okay, and then of course by the theorem, by definition, this is actually written of using residue theory, that this is 2 pi r multiplied with your finite sum of the residues. So I'm just going to denote this as n, j is equal 1 of the residue of your function f of z, and then at the z sub j, so ever how many poles are in your, your function that you're dealing with. Here in this case, we have 1 over z squared plus 1. You decompose the denominator, we have z plus I and z minus I. Your poles are going to be at z is equal to I and negative I. With that being the case, we note that z equals I lies inside of our contour that we're dealing with, so over here, so that's going to be I, and then down below is going to be negative I, but that actually means that this is not inside our contour, so we can actually just disregard the negative I value that we actually decompose from here. So really, we only have one pole to calculate from over here of that residue. So with that, before we get into that, we have to actually take into account our semicircle arc length f of z of the c sub r. As we know that if we were to take the limit of this entire integral over here, so that's actually going to approach 0, but let's actually get into the whole, calculation slash proof of that entire thing. So this involves taking the maximum value of our contour inside here. So starting things one at a time, of course. So I'm actually define, of course, this parameterization c sub r. I'm going to let this be the set z equals our capital R I t, so using Euler's formula around in this, the unit circle to that extent, with 0 and then t, and then, 0 less than or equal to t, and then less than or equal to pi, since we're only dealing with the half circle over here. With this in mind, then we know that if I just take the modulus at any z that we're actually calculating with that radius, so that means absolute value of z, the modulus of z is basically just the radius, capital R. So of course the next thing will be I take the maximum, so the modulus of our function f of z, so 1 divided by z squared plus 1, then we can set that equal to, so that's written as 1 divided by the absolute value of z squared plus 1. Then of course we can create this bound to say the same thing as, just write this as equals for now, and then everything together that we'll combine it with the inequality. So this is 1, and then modulus z, then outside that square plus 1, then plug in that we said that this is equal to r from integrating along that line, so this is basically just 1 divided by r squared plus 1. So with that in mind, so now we can actually just jump in all together to calculate this limit over here that approaches 0. So the limit as capital R approaches infinity of, now I just take the absolute value of the entire integral on that semicircle arc right there. So the absolute, or the integral of c sub r of 1 divided by z squared plus 1 and then dz. So of course I can create this lower bound, so it's less than or equal to capital R approaches infinity of that limit, then c sub r, then I take the absolute value of inside of our integrand, so 1 divided by z squared plus 1, then dz, then now just put in that bound yet again, create that little bound yet again, so the limit as r approaches infinity of the integral from c sub r of 1 divided by r squared plus 1, then that's supposed to be dz. Then if you were to calculate this on the bound, so that's basically just calculating the arc length on that unit circle on the top half right over here. That being, of course, is just going to equal to pi times r. So that means the limit as r approaches infinity of pi times capital R divided by r squared plus 1. Take that as approaches infinity, and therefore you're just going to get that it's equal 0. So with this being the case, this eliminates that, and now we're just left to calculate this integral over here. Basically, we have 1 over x squared plus 1, which we said from here by using residue theory. So now all that's left is just to calculate that residue. So pretty simple from there. So going back, so we have now the only thing left is, so I have the integral negative infinity to infinity. So 1 divided by x squared plus 1 dx is equal to 2 pi I. Then we only have the only pole to calculate at z is equal to positive I over here. So f and then z is equal to I. So we know that calculating poles is basically the same thing. So is the limit as z approaches some value of that pole, which is going to be I, of z minus I, and then times your f of z function, which being that we decompose this to say that this is just z minus I, then divided by z plus I, and then z minus I. This is going to cancel out. Let me get wrapping on the marker for this. I know I forgot to write the limit, but that's okay. So if we just plug in I there, that means I have that this is equal to just 1 divided by 2I. Okay, so now just put that back in. So that means now I have 2 pi I, then multiply with 1 divided by 2I. And so therefore the 2 and the i's cancel, and we're just left with the final answer of just pi, which is exactly the same value as we calculated from the easy way of calculating the improper integral. So just like that, that completes everything. Which method do you think is the fun, the complex or the easy way? You just let me know in the comments below. So there you have it. So yeah, that's pretty cool if you ask me.